Change still occurs in a buffer system. It's just because it's dealing with an equilibrium, and I'll show you how the equilibrium works. The change will just be really smaller. So instead of dropping from 7 to 3 or 7 to 1 with a couple of drops, it just goes from like 7 to 6.9. Your blood is loaded with natural buffers. Any slight change in pH. In fact, the pH of your blood controls whether or not you can absorb oxygen. Any of you in Biology 12, Anatomy and Physiology? We're in that. In the pulmonary system for the lungs, at your tissues, because there's a lot of metabolism going on, it tends to be slightly more acidic. So at a pH of 7.38, hemoglobin will actually change its structure slightly to release oxygen and bind CO2. At your lungs, where it's not quite as acidic, the pH is 7.40, and at that pH, hemoglobin changes its shape so it binds oxygen really well. That way you are absorbing oxygen where you need to and releasing it where you need to. And these are very small changes. If you undergo, if you manage to do, say, you wanted to go on a diet and you think, I should just eat meat and butter, so you're going to undergo the low carb diet, and you manage to get to 0 carbs, you'll put yourself in what's called ketosis. Ketosis means you can't properly process the protein, and you're releasing too much acid. Your body will go into acidosis, and then you'll go into a coma, and then you'll die. The goal of a low carb diet is never to have 0 carbs. If you do that, that's actually incredibly dangerous. The low carb diet was invented for people with epilepsy. We don't know why, but if you have epilepsy and you go on a low carb diet, it reduces the amount of seizures that you have. And it's a low carb, not 0 carb. And it was particularly used for people in which medication didn't work, because it doesn't work as well as the medication does. Okay, everybody got the notes from there? Describe the procedure describe the composition of an acidic and basic buffer and outline a procedure to prepare each. So here's how we do it. You get a weak acid and its conjugate base. In this case, we're going to use vinegar and sodium acetate. And we add both of them into solution. So here, write the equation for CH3COOH in water. Quickly do attendance. Attendance, there it is. We have Andrew, Ashley, Ella, Etienne is not here, Gleb, Josh is missing, Katie is here, Lavina is here, Max, Neha was there, Nick, Sam, Sonia, Chaz, and Tia. Okay, Andrew,
Hi.
finish off this equation for me.
I wrote CH3COOH plus H2O. Makes CH3COO minus plus H2O plus.
plus.
H2O plus.
Sure. Now what we've done is that we've taken acetic acid and we just added a bunch of it into solution, and it's done this equilibrium, and so we have lots of this, right? And then we added, dropped that into solution. So what else do we have lots of?
CH3CL.
Yeah, so we have lots of that. Now this is a regular equilibrium where we just added that or just added that. We'd only have lots on one side, but now we have lots on both sides. What do I? I'm going to cross this out. What happens? Let's double check. What happens? I'm going to cross that out. If you add H plus. In this system, if we add more acid, what will happen?
It goes to the left.
It will go to the left. Why? To maintain the equilibrium. Chef's writing in red with a red question. Let's change the color. Purple looks good. So it shifts left. So in this particular way, it goes like that. You've added more, and there's lots of that to react with. This offsets. A drop in pH. We added acid, but we used the equilibrium because we have lots of acetate for it to react with, and the equilibrium just undid what we did. So we're using Le Chatelier's principle. For this one, let's not say in an acetate solution. Let's say what happens. If you add NaOH. What happens if you add NaOH? Oh. I think that looks perfectly reasonable. What are you talking about? Offsets drop. Ooh, none of this. It didn't even give spaces. And I think to also just belabor the point, we have an increase of concentration of H3O plus. Therefore, it shifts left. Just to remind us that this is all Le Chatelier's principle. It's shifting left because we're increasing one. If we add NaOH, which way is it going to shift? It'll shift right. Why?
I just remember it that way. It's like the opposite of H plus.
It is the opposite of H plus. So, well, if we add OH minus, what is the OH minus reacting with in this? What does it annihilate?
H3O.
H3O plus. What happens if you OH minus? Plus H3O plus makes water. So it decreases the concentration of H3O plus. Way back when you were doing equilibrium questions on old exams, you would come across questions and you'd come and ask me, well, Mr. Neufeld, none of these things are either adding something or precipitating something. How does this affect the equilibrium? And I would say, oh, but they're adding a base. So you have to know that that reduces H plus. We hadn't done acids and bases yet, so that wasn't immediately obvious. So we are reducing this in this particular case. So then, as Nick says, it will shift right. offsets increase in pH. Sorry, were you just asking me to move?
I know. I'm over.
What would happen if we made the buffer and we only used acetic acid? We just got some vinegar and said, there's your buffer. What could it do and what could it not do? So when we made the buffer, we added both acetic acid and sodium acetate. What do we just have? CH3 I won't react with H2O, do the short form. What do we have a lot of? We have lots of this. What else do we have a lot of? Is there anything else we have a lot of? No. We have a tiny amount of this, whatever the Ka is. So what could we add to this that it would be able to accommodate and buffer? Which way could it shift for a relatively long amount of time? Yeah, you could shift it this way. So you could add, what would shift it this way? Base. It's acid. It would make sense that it could take a lot of base. So you add base, it shifts, you add base, it shifts, you add base, it shifts, you're good. But what happens if you add acid? Which way will it try to shift? Left. It'll try and go that way. Is there any of this to react with it? No. So it'll just, the acid you add will affect the pH. So if you have a weak acid or a weak base, you essentially have half a buffer. If you add both, you now have lots on both sides and just a tiny amount of that. So now it can move back and forth. You can either decrease it or increase it, and these will react either way to center that pH around the, whatever the value is for that particular weak acid, weak base system. So this can only buffer base, no weak base or acid to react with. If, I didn't mean for that to go quite that close. So if we wanted to make a buffer system, come up with another buffer system, any buffer So we have HF. So you'll add some of this. What else would you need to add? F minus. How would you add it if you went in off the shelf?
NAF.
NAF. Add NAF. If the equilibrium has enough on both sides, so you have lots and lots. Then there's something there for the acid and base to react with. Acid-base buffers can be overwhelmed. At what point would this be overwhelmed?
When there's no more HF or F to react with.
Yeah. So you could have a 1 molar buffer system, in which case you added a mole on per liter on both sides. Once you've added more than that, it's going to run out. Our lakes and streams that have dissolved carbonates and a variety of other dissolved minerals in them have a natural buffer system. They have weak acids and weak bases just floating in them. Their buffering system tends to stabilize the lakes. You add a little bit of acid, they will survive. If, however, you have a mining tailings pond and you release that into the stream and then it goes down into the lake, you will kill that lake. If you continuously get acid rain over a region and it keeps raining on the lake, then slowly over time, rather than quickly, but slowly, that lake will be dead. Canada used to have a number of dead lakes in Ontario. Due to the amount of factories in the United States, they would release nitrogen and sulfur oxide gases that would float over to Canada. They would mix with water and they would make nitric and sulfuric acid, and then they would rain down. Now, not rain down and you're burning. Instead of a pH of 7, they're a pH of 6, 5.5. You know, not even as harmful as a lemon, but continuously over time in large volumes, it would wipe out the buffering systems, and then the lakes would just slowly grow more acidic. Because if the acid keeps coming in and the water keeps evaporating, and you add more water with more acid, and the water keeps evaporating, the lake just becomes more acidic. Question?
No, can you scroll up for a second? Okay, perfect.
We have a lot less of that now. More factories have pollution controls. So naturally, what we figured out to do to improve that is that we shipped all of our manufacturing over to countries where there were less pollution controls, and now there just aren't any factories in the States anymore. What would the pH of this buffer be? Anybody want to guess? Or even roughly? I'd actually have to look it up myself. But even if you can give me a ballpark. Oh, where's my data table? Oh, someone wrote it last day.
There's 5.
About 5? Yeah, I think that seems reasonable. If I recall what the Ka is, let's go for, yeah, it should be around 5. How did you get that?
So the K is times 10 to the negative 5.
So everyone can go in and get the exact amount. There it is. Whoa. That's the Ka. It'd be roughly around 5, but we can do better than that. What is the exact pH of this buffer system?
4.7.
4.74.
7.4.
2 sig figs. The pen, I gotta restart this computer. The pH is equal to the pKa for the buffer system. And so this is why you can just pick your buffer. If you have a system, a biological system, and it works at a really acidic pH, you want a pH of around 3, well then you'll use a phosphoric acid sodium dihydrogen phosphate system. And that's your buffer and your acid and weak base. Oh, how was this calculated? I meant to write that in there.
Mr. Nizzle,
Yep,
so when it's saying buffer center, is that like when it turns back into like green?
say it again.
When it's asking for buffer center, is it turning back into like green? Like,
Yeah, so like when I added it, it like it went fake purple at one point, and then you had to swirl it and go back. So that's the equilibrium reacting.
okay.
Maybe we'll walk. Now this is the pH of the buffer. You could do the exact same thing with the Kb, but you don't get the pH of the buffer. What would you get? pH of the buffer. So it works either way. Calculate the pH of that buffer system. I'll ask someone, and let's add a couple other ones. So what are some common ones? Ooh, boric acid. And what's another common one? For an acidic one, the oxalic acid, but that's a lot to write. Nitrous. NH3. So what is I need more caffeine. Drugs.
Can you go up a little?
Like on the screen, please.
Yeah, sorry. That was deliberately annoying because I was looking something up. Higher?
Really good job. Thank you.
Okay, I'm going to ask a completely random person for these. Completely random person like Andrew Kim.
9.25.
Huh? You were ready. How about the next one? Katie.
I didn't get that far.
Oh, I'll wait. I will get someone else to do the third one. Yeah, the third one is Nick Meyer.
I'm still trying to figure it
Oh,
out.
okay.
Is that Biotherms?
BO3, yeah. That's someone after rugby and rowing, and then they didn't wash their uni for 3 days. We did have the joke was it's BO times 3. We did have someone, a cleaning staff, who called hazmat services because they thought they found a dead animal, like a larger than a rat, under the bed in one of the dorms. The smell was so horrendous. on it, they couldn't see it well, so they came in like geared up. It was someone's rowing knee that they had worn several times, and then chucked into the bed.
Wow, that's just kind of slow.
Charlie Dortovich.
That sounds like a cat thing to do.
It's just the kind of. He actually was on reality TV for a while. Very funny man.
9.25.
That was this one.
Oh, yeah. Wait, can you scroll up a little bit?
What again?
Yeah. 9.14.
9.14.
Yeah.
Down. Good. 9.14.
That's the second one.
That is.
9.14 is
Hold it. Which one did you give me?
Second one. Edge.
Oh. Katie, can I switch you to the last one then?
Yeah, just give me a second, please.
Actually, here's a good time to chat. Chat GPT. What is the pH of an ammonia/ammonium buffer system?
3.34.
3.34? Perfect.
Wait.
Jeez. Where's NH4?
It's not working.
Oh my gosh. ChatGPT very correctly gave me the Henderson-Hasselbalch equation for calculating the pH of a buffer when the concentration. So you take the negative log of the Ka, it works, but only works if the concentrations are equal. There's a whole equation if it's not equal, which we don't tell you in grade 12. ChatGPT correctly figured it out, but confused Ka and Kb and got the actual answer completely wrong. So it got about halfway there. It's getting more useful. It used to get the equations wrong. Today is the worst it will ever be. Identify limits in the buffering action. What are the limits of this buffer?
Well, in which one? You have three.
Any buffering system. Like, what is the limit of buffers?
Just the lowest concentration.
The lowest concentration?
Highest.
Limited to. You're on. I think I know what you mean, but phrase it in a way. I'll put Gleb in charge. Gleb, translate. What do you mean?
I've been paying attention.
I'm not paying attention.
I've been doing the last couple of questions.
Oh, well,
I work from home.
let's go all the way back to here. What would limit this buffering system? We have HF here, we added NAFs. When is that system going to stop working?
Once there's too much,
Once one of them runs out.
Once one of them runs out. So if we go back to here, limited to the moles of weak acid and weak base present.
Mr. Newfield, isn't that only when you're buffering strong acids or bases?
a buffering, if you add a weak acid or weak base, it will still buffer it, it will still work. But now you have two equilibriums.
Yeah.
It's not as much of a problem because it's not going to create as drastic a change. But a weak acid is still going to react with a weak base, and that equilibrium will keep going as long as there's H plus. It's just a little, it takes a little longer.
But it won't fully use up one of the buffer sides, right?
Well, it depends how much, because remember our HCl and HCN question from the other day?
Yeah.
It'll still eventually
Yeah,
go.
because HCl is a strong acid. That's
No.
why it's that weak.
But the amount that you required was completely, here. Let's say this is a buffer,
Yeah.
and you have lots of that, and you have lots of that. And you add in a weak acid.
Yeah.
You add HF.
Yeah.
HF does this,
Yeah.
and this then increases.
Uh-huh.
What does it do?
Left.
Goes that, which means that this decreases. What does that do?
Goes left.
That means this increases, and it will just do this until all of this is gone.
So does less go back.
So,
But wouldn't, like, because the A minus, wouldn't that, like, because it's in equilibrium, right?
Yeah.
So it won't react with all the hydrogens. It will only react until the equilibrium is reached, right?
yeah, and when the equilibrium's reached, you're basically at its Ka again. The amount of change will be
So
very
it
small.
won't fully use up the A minus.
Oh, it won't, hold it. It will use up all of that if the concentration of that exceeds the concentration of that. This only works for small amounts. Am I misinterpreting your question?
Maybe a little bit, that's fine.
Because I think you've asked this in a different way before. So only small amounts. So, we are a little worried about the buffering now in our oceans. The ocean is slowly becoming a little bit more acidic due to the increase in carbon dioxide in the air. So you may have heard that carbon dioxide is a worry because it warms the planet and it creates global warming or climate change, and that will melt. Who cares? Everything will still live. There'll still be land. It's fine. It's fine. Everybody will have to move, and most people will suffer. But life goes on. If it becomes too acidic, then the carbonate shells of every sea creature at some point will exceed their ability to make them as fast as they dissolve, and they'll all die. And if they all die, that means the ocean ecosystem will collapse. And the ocean ecosystem feeds the land ecosystem. So then that starts a collapse of the land ecosystem. So, whenever you can, stop buying things. If it'll work for an extra 2 years, so we can release a little less CO2 and maybe convert to nuclear power, we can stop the amount of acid that's dissolving into our ocean, because CO2 plus H2O makes H2CO3, which is carbonic acid, and as this increases, we keep shoving the equilibrium over there, and the chemists are really worried. They're more worried than the climatologists. We're not there yet, and even if the weather gets really bad and we get really warm, we really don't want to go that far. So use your iPhone for an extra couple of years before you replace it. Okay, describe qualitatively how the buffer equilibrium shifts as small quantities of acids or bases are added to buffer. We are going all the way back to equations of concentration. We have this equation. I'm going to do, let's make, I'll keep it the same color scheme. This is H plus, and this will be OH minus. Assuming this is a buffer system where you have lots and lots, I go along and I get to this point, and I add a bunch of acid. What would that look like on the graph? we go up. Let's spike up. These are our old graphs from equilibrium. And then if I was to make a dashed line, I want a black dashed line. Then when that goes up and the equilibrium reacts, what does it look like? Zoom. I like that entire motion. It goes, does it go all the way to the line?
No.
No, it just settles out somewhere above it depending on how much you added. So yes, the pH will change. The pH will drop a little bit, but it's not going to drop as much as it did because the equilibrium system reacted. What would the OH minus graph look like? Down, down. So we do the OH minus, drop, same thing. I don't know why I have the equation above them, but what happens to the graph of all species after an acid? We've already did that on graph. Good. Everybody still writing it down? Hello? Put your phone. Okay. What are some uses of buffers? The lake. So, environment. Keeps lakes at neutral pH. This is a natural buffering system. Everybody freaked out, what was it, 12 years ago now? And the part that does it is this is limestone buffering. It keeps the lakes at a neutral pH, so that's a natural one.
Isn't it bad to swim in lakes when they have too much limestone?
Is it?
Because it like eats away at your bones or something.
Oh, if you haven't, eats away at your bones?
Like disintegrates. I feel like that's, you know how there's like the quarry in Shawinigan?
Yeah?
And people like stop swimming in it. Like it closed down, but also like if you go in it for too often, then the limestone like damages your bones or something.
But the bones are inside of you.
You know?
Doesn't make any sense.
So like you're like.
They stopped swimming there because they found a body.
Well, someone died, yeah, but also like the limestone.
I'm right after this. I'm looking this up because
Yeah,
I could see if you drank it, and then it was slightly basic, and somehow that constantly used something up, and you drank it. Like it is, for example, in a similar way, it is unhealthy to drink distilled water. Why? Doesn't have all the minerals. And when it goes in your body's in equilibrium. If the water is lacking those minerals just equilibrate out of your body into the water, and you constantly leak minerals. But limestone lakes, like if the pH is, unless you walked out with chemical burns, like the bones are like, yeah, that's wild.
Mr. Neufeld,
Yes.
what happens if you drink heavy water?
We long thought that it wouldn't do very much because chemically it reacts the same.
Yeah.
You drank what?
Heavy
Heavy
water,
water.
like made out of deuterium. But there are a lot of enzyme functions that rely on speed of the hydrogen. If you drank it for long enough and you started replacing your hydrogens with heavy hydrogens, someone went into detail on it, it would actually eventually start affecting your enzymatic reacts and it would become poisonous. So a couple drops, no big deal. Drinking it long term, like you somehow have access to a multi-trillion-dollar supply because it's
What
very
about like
expensive.
1 cup?
It's fine. Pretty sure you do. There's also the buffering in lakes. There's a CO2 HCO3 minus buffering system. Can anybody think of any biological systems?
Blood.
Blood. What else needs to be kept at a neutral pH so that your proteins don't denature? Hemoglobin in your blood? Ooh. Stomach? Your cells? Inside your cells themselves must be buffered, just like your blood must be buffered. The lung hemoglobin system. We now have, Sam, do you have a question? We now have GMO, like yeasts, to make things like insulin.
What's after that? It says HB.
HB, hemoglobin.
Oh.
If you're not in bio, that might not mean as much.
No, I am.
Okay, because your hemoglobin, do they still teach that your hemoglobin, they teach you about oxyhemoglobin, carbaminohemoglobin, and reduced hemoglobin?
No, they don't teach you
Just
that.
In physiology and anatomy?
Yeah.
You just learn that hemoglobin. Like,
Oh, okay. 98% of your oxygen is carried by hemoglobin to your tissues.
that's all you learn.
But at your tissues, that's actually CO2, about 25% of the CO2 is picked up directly by hemoglobin and brought back to your lungs. So not as much as the oxygen, but a significant portion. And in that process, there's quite a lot of acid being released, and your hemoglobin will pick up the extra hydrogen and bring it around as well. So hemoglobin's doing a lot of functions in there. And this also acts as a buffer because it's absorbing some of the extra acid. You are always becoming acidic to the point that our buffering systems are really good at dealing with extra acid. Because if you have too much base, you just wait a while and it becomes acidic. Industrial applications. So this is a biological system that we're now using for industry. If you know anybody who has diabetes and they're getting their insulin, safe human insulin is produced through genetically modified organisms on an industrial scale. We have to buffer those systems, make sure the poor little critters don't die. Human growth hormone, all sorts of drugs are made this way. But there's an even more important one, the most important thing in the entire world. Cheese.
But what about like wine and stuff?
Yeah, wine is okay. But cheese. Know anybody who's lactose intolerant? Do they still eat cheese?
Yeah.
Cheese is more important.
And kombucha.
Ooh! How do you, I can never spell kombucha. There's a, if you really like kombucha and you're interested to get in fermentation, you can make your own pickles, you can make pickled onions. There's all sorts of things. You just put it in a jar, mix it with a little bit of water, add some sugar, add some vinegar, and just let it sit under the right conditions, and you can make a ton of really tasty foods, including kombucha, if you know what you're doing. A friend of mine, because we're all chemists, made mead. Do you know what mead is? Honey wine, except mead is its own drink. Under modern regulations, you can't make proper mead anymore because it has to be too sterilized so people don't get sick. So you can't make it the traditional way. So you can't buy proper mead. But if you know how to make it, it just takes honey and some organisms and you can make proper, it tastes amazing. And I don't even like alcohol. Oh, and there's the other stuff like mining. Because we want to usually leach out the elements. All of these are example of what process? Fermentation. Fermentation. Anyone's a missing enzyme activity? Oh, why is it important to buffer your blood and your cells? What happens if it's not buffered?
Like
Change.
things you eat, they get changed too much.
Things you eat make, but what does it damage? There's a special word for it. I said it. It's the proteins in your cell that change the most.
Enzymes.
Enzymes. And what do they do if the pH is too high or low?
They die.
They die. Does anybody know the special word for enzyme dying?
Oh, I knew it that way.
If proteins,
Desaturate.
you're close,
De.
enzymes are proteins,
Denature.
denature, are in extreme pH, they denature. And denature is just a really fancy word for cook. They change their shape and they cook. If you take egg white and you cook it on a pan, it goes white because the proteins unraveled and then stuck together, and then light doesn't go through it anymore and they all denature. If you take the same egg white and you drop it in acid, wrong pH, it goes white because it's cooking. If you take meat and you put acid all over it, you're denaturing the proteins, you're pre-cooking the meat. You're just doing it chemically instead of with heat. If you take your eyeball and you very carefully scrape off the protective grid off your microwave, and you stick your eyeball to the microwave, you will not get cancer. Cancer-free, you'll be fine. The microwaves do not cause cancer. You can, however, hard boil your eye because the fluid inside your eye is very similar to egg white. It's a clear, translucent protein mucus mix. And you can hard boil it till it's white. And the only thing you do after that is eat it. Like, you can't fix that. It's done. So. Does anybody know why the grid actually protects you against the microwaves?
What does? What grid?
The grid on your microwave, like it's got those little hatch things.
Not all of them have that.
What about the
It
wavelengths?
alters the wavelengths. It
No,
makes it
it's-
smaller.
You're very close. It doesn't make the wavelengths smaller. They're just smaller than the wavelength.
Yeah.
So the wavelength just physically can't pass through. So if you can make your microwave work with the door open, please don't do that. It's not like an oven where heat's just escaping, which some people have thought and gotten themselves into trouble doing this, because now you're irradiating yourself and it's damaging all the proteins. I know someone, this is a story she was told. She worked for Canadian forces. She was stationed up north at one of the NORAD radar systems to detect incoming ballistic missiles from the USSR, back when the USSR was a thing. They were cold because it's north and it's Canada, and they found, question?
No, I'm just saying, no.
Go ahead, say it.
New weapon, drop open microwaves.
That's actually a real weapon they tried. They just can't aim it properly. This person stood outside the rotating radar thing. They noticed they were warmer when they did. Probably because the microwaves were warming up their body. On the weekend, they got into a bar fight. And after the bar fight, they had bruises. Like one hit would just make the bruise spread over all of a huge section of their body because they were damaging all of their cells. And all of their cells were breaking down because of the microwaves very slowly. They were cooking themselves.
Why did you quote derivative?
Pardon?
Why did you quote derivative?
Why did I quote derivative?
Yeah.
Denatured.
Oh,
Denatured. Okay. This is the chemistry gnome of good luck. We are now done PLOQ. We're going to do R next day in one day. And then we'll be done all acids and bases, and we will start redox. Your test on all of acids and bases will be immediately after the break. No, I'm Mr. Newfield. Are You Serious is an Australian actor from the 80s.
Are you supposed to study on this?
No, you're supposed to be studying continuously all the way along.
That's so weird.
You had APs. I wasn't going to schedule it during this week. But LPs are now over, right?
Now AP's are after break 2.
What? What? No, but it's not an important one after
They
break.
go on
Yes,
for
AP
2 more
Physics.
No, but who has one after break?
AP Physics, 24.
You don't study anyway.
I'm not even writing the one on 24.
Yeah,
I'm wrong.
there you go. I double checked who. 10 push-ups, 11. 10 push-ups right into you. I cross-referenced, I thought all the APs everybody in here had, and I don't think anybody has any over the break. Am I lying?
Ah.
It is. Now I gave him a chance to show off. So, yes, there is a test later. I'm sorry about the timing, but I didn't want it to interfere with your APs. No,
It's like a unit test on the whole. Like,
all of acids and bases.
What unit?
JKL, MNO,
Can I have
PQR.
my phone to write this in my notes?
Oh, yeah? Yeah. Oh, I like how you're coloring in the note. Did I tell you the story of the note?
No.
I was in chemistry, I think it was 232. It was a 3-question final exam. I looked at the first question and I thought, I just went like panic attack because I didn't understand it. And I studied. I was like, I don't know what I'm doing. Turned to the second question. Couldn't understand what it was talking about. So just to calm down, I drew that noun, or a version thereof, and wrote a little story about the gnome on the second question. That's all I did. Turned to the third question, and it was about catalysts, and I also didn't know what it was talking about. But I was doing chemistry and biochemistry, and every enzyme's a catalyst, and I knew a ton about enzymes. So I just wrote absolutely everything I could think of about catalysts and enzymes and how they worked, drew diagrams, and every time I panicked, I went back and looked at the gnome and then went back and did it. I got one of the top marks in the class because apparently nobody else knew what the exam was talking about and it was graded on the scale. So 38% turned out to be an A. Never panic, write down everything you know. Believe in the gnome. I had a student come back and say, I said, how are you doing in chemistry? First year, he said, I'm doing great. I said, what's your mark? He said, 42%. And I went, oh, and he said, don't worry. The highest mark in the class is 43. I'm doing really well because it's marked on a curve. So 42 is an
Isn't
A.
that like
They should bring
teacher's
that back.
problem?
Pardon?
Isn't that
If
like
you have a
teacher's problem with that?
50,
No, like university teachers,
you get a
they don't say 86 is an A. They just take all the marks because all your marks, if you have a big enough class, your marks will form an average distribution. And what we say in high school, because we have smaller classes, is we say 86% and above, that's an A, right? Here is 50% and below, that's a fail. And here should be a C+. This was the original idea behind the Canadian marking system. The average should be 67.
So you want everybody to take
Not you want, it's just if you tested everybody in the province on a provincial exam, that's what they geared it to. At university, the professor just goes, he gets this graph and then just goes, oh, that's an A. This could be 23%, and anybody with 9% and lower is failing. Like they just redo it according to the curve.
which if you get a 50 you didn't fail.
Yeah. So it's not, at that point, because the professor, like what I try to do in most high schools, we scale the tests to the difficulty of the course. A university professor may just give you the hardest questions they can think of, knowing it will be too hard, and expecting only 42% as the highest mark, just to see what you can do. They don't want to put a top level on it. So there's somebody in there that can answer lots. The opportunity is there. If you can only do some, it's great. You just have to not give up. Also, some of them are weirdly angry about the number of people in their class because they get paid to do research. They don't want to teach. So if you just get scared and quit, they're like, that's a problem for the bursar that's trying to make money for the university, not a problem for the professor. The professor just wants to go and do some chemistry.
So you have 70, but it's the highest grade in the class. Do you get 100?
Yeah, can. Ottawa professor of mathematics, he was at University of Ottawa? He taught statistics, and the class carefully read over his syllabus and realized, because he marked on a curve and the way it was worded, if everybody got 0, then everybody would get 100%. So they all talked about it, and they're like, don't you dare answer a question. They went in, and nobody, because if one person answered a question, they would have gotten 100%, and everybody else would have gotten like much less. So everybody went in, wrote their name, they left, everybody got 0. The professor, like this made the news, granted it to them. They said that was very clever. You understood the course very well. He gave everybody 100% and then rewrote his syllabus so that if it's tried again in the future, if everybody gets 0, then everybody gets 0. But for that class, everybody got 100%. Legendary class. Yeah. Okay, the rest of the class did work.
Yeah.
Class
A
of
whole minute
Yeah.
or 30 seconds.
Can you mark this class on the group?
Pardon?
Can you mark this class on the group?
I could. You kind of already are. Well, like in a proficiency system, what's the lowest grade you can get? No, not yet emerging. How much is not yet emerging worth?
Can you fail with proficiency?
No.
You have to work really hard. What is not yet emerging worth?
48.
45. So if you hand in a worksheet with one thing on it and you get like 1 out of 50, that is worth 45%. So all of these get shoved up to here. And so the curve is actually distorted under a provision because they don't want to fail anybody. But, you know, a 52% is not going to get you into university.
I get it.
It's
Why
not
do you
that.
want to fail kids? Like, if you're stupid, you should fail. It's just fact.
It is not so much about not failing kids. At a high school level, if you don't pass, there's not like there's a resistance to that. The proficiency system is mostly for elementary, where it's been shown that keeping kids behind a grade really seriously impacts their growth. And they'll pick up the stuff later.
Why do they use the prize?
We're the only ones doing that. I didn't say that though, and I'm going to go edit the recording right now because I didn't say a thing.
Hey, thanks, Nick.
You're welcome.
Could I start with the test now?